Welcome, everyone, to episode number 8. Today, I wanted to talk about a topic of guardrails on artificial intelligence. And I think that's something that there's some general concern about that. And seeing public groups, I just got a recent invitation to a Canadian group. They were getting some AI companies come together to talk about topics related to AI. I've seen some groups in Europe and UK coming together to talk about ethics, guidelines, regulations. So I think it's a little bit of a timely topic. I'm going to talk a little bit granularly about guardrails and the technical details of that. That's one of the patents that Daisy has granted is around the concept of putting guardrails on artificial intelligence. And so I wanted to talk about first, if you're thinking of applying some learning that you've created from data. So let's start with the laws of physics. So let's say we have a general theory of relativity. And from that, physicists postulate that's how the universe works. And they say, okay, we think this theory now shows that black holes can collide. We've never seen that before. The model hasn't, this is a consequence of that model. We've used that model to calculate and measure and observe things that are local to us. And now we're saying, okay, well, does this model predict black holes? And so experimentally, astronomers go out and look for this, built LIGO, and decades, 100 years after Einstein came up with theory, we found some evidence that the theory is correct, and we actually were able to measure the collision of black holes and measure gravitational waves and things like that. So that's kind of how science works, is that you come up with a theory. The theory makes hypothesis that this should be happening, and then you seek experimental observation to try to validate that the theory is correctly explaining something you see, or you create a theory to explain an observation that you can't otherwise explain. That's kind of how you expand or prove that a theory works or not. Now, so if you build a model with data, what are the guardrails? And in Daisy, we've built theories. Our theories aren't so ubiquitous that we would say, or so all-encompassing that we'd say they explain the universe. Not like the laws of physics. We're not doing anything that grandiose, trying to explain how business works. But because some of it is based in data, it's like, what is the range of applicability of the learning that you get from data, or the learning that you get from a theoretical model? When can you apply it safely, and when can you not apply it safely? So if we think of another example, think of like a baby learning to walk. As you observe your children walking, and maybe when first time they go up or down a step, the baby doesn't say, great, now I can jump off a cliff. The baby doesn't immediately go, I've done one step, now I'm going to jump off the second floor landing because I can do one step, right? How does the human being learn? There's still fear and limitations, and we go one step at a time. We go from one step, we repeat that multiple times until we're very comfortable with that. And then we go to 2 steps and 3 steps and work our way up to a large range of experience. So if you think of experience, and I'm a geometric thinker, so I think in 3 dimensions. So you think of a 3-dimensional graph. If you think of a ball, our experience is inside the ball, right? So that's our known and lived experience. And if you think of data, if you're building a model from data, supervised learning, and you plot your data, think of a ball. In 3 dimensions, it would be ball, and if you have n variables, it would be an n-dimensional sphere. That's the applicability of your model. And in some parts of that sphere, you might have more data points than others. So your experience is not necessarily uniform in that ball of data you have. And so if you have a real world data point now that's outside of your ball, or you're predicting or you're optimizing a decision, let's say you're doing price optimization in retail, and you're picking a price for a product that's outside of that ball of experience, can you confidently say that that will be correct? Because this is now a data point that's far away from other data points that you've observed where your model has done its learning. And learning from data, you would have to have some reasonable density of data to confidently say that these patterns are real. So as soon as you start going outside of your domain of experience, I think that's now where things start to get a little dodgy. And that's where we start to think about guardrails, right? And so I think that's where we can bring some engineering concepts to play. And similarly with a mathematical theory, like Daisy has a mathematical theory of retail, there's a domain of experience again, driven by that data ball, which are all the decisions that you've made. What is that spherical domain of where you've made decisions? And can we confidently make decisions? We can confidently make decisions that are inside that experience, lived experience, or we have lots of data and lots of density of data, and we know how things behave. Your probability of being correct is high. As soon as you start to move away from that experience, things get dodgy. So whether you have a database approach or a theoretical approach, when you move away from known experience, things get concerning. Now, as I said, in the laws of physics, there's no, if we get the black holes colliding wrong, what's the downside of that? There's intellectual knowledge. No one's going to die because of that today. Maybe the universe might end or something, but these are very low probability. We're not, there's no fear of being wrong. There's human pride if you're an academic, I guess, if you made a claim that turns out to be wrong. So there's that at stake. In the case of a baby, your child could get injured if he or she decided to jump off 10 steps instead of going one step at a time. If we're making medical diagnoses now, we're taking a data point with a person that has some symptoms that we've never seen before. We're now making a medical diagnosis or recommending a treatment that's outside of our experimental data or measured data. That could be dangerous. We could be doing something we don't know. So how do we deal with that? And if you think of engineering examples, we have statistical process control. We set limits, upper control limits, lower control limits on things we measure. So we would measure the system. We have, let's say, a steel plant, and we know that we have molten metal flowing through some conduits in the plant, and we have cooling water, and we measure temperature, pressure, flow rate, and we have continuous measurements real time. We've been measuring for years, and we know within statistical probabilities, plus or minus one standard deviation or 1.5 standard deviations is statistically typically an outlier is 1.5 standard deviations away from the average. As long as our system, all of our system measurements are within the plus or minus 1.5 standard deviations, or maybe we call these control limits, upper and lower control limits from the mean. As long as we're within those control limits, we're feeling pretty good. The operators in the control room are seeing all green lights on their dashboard when everything is within those control limits, and we're measuring everything. As soon as you get outside of those control limits, maybe the light goes yellow when we're, at 1 standard deviation away from the average. Okay, something's going on. The system is behaving slightly differently than normal. Let's keep an eye on it. Let's make some adjustments, try to get it back within control limits. We see red lights. We get to 1.5 standard deviations out of the norm. We're freaking out. We're hitting emergency stop button because the steel plant will explode and blow up, right? So let's bring that same thinking to AI systems. You're building supervised learning models. You have 1,000 variables that you build for doing your modeling. You're building a credit approval model. You're building a model for, is this person sick or not? You're building a model to say image recognition and what is this picture? A large language model, maybe whatever you're doing. You should now be tracking all of the metrics that lead up to the final outcome. So you have a mathematical equation. If you have a deep learning model, it could be some horrifically complex model that has billions of parameters. You should be tracking all of those parameters like a statistical process control model. This is my conjecture. This is one idea. I'm not saying that there's other ways to do this, but our idea would be to have a statistical process control on every metric in your system. So if you have 1 billion parameters in your model, you want to build 1 billion statistical process control charts to track, are these parameters within normal? As you have new data coming in every day, you're collecting new data. You're collecting the properties of that data, and you should even go further back than your model. Your model has 1 billion parameters. Is the model behaving like we have seen in the past? As soon as the model starts behaving differently, you get a lot of metrics that are out of norm, that are in that 1.5 standard deviations or in the warning area. Then you might start to lose confidence in the predictions that your model is making. And going further back into even before you feed the data into your model, tracking the data, the properties of the data. How many records did I collect today? What was the average value of each of the variables and the records I collected before I even do any transformations or calculations to the data? At every step in the data engineering process, you could track metrics to say, yes, we collected 1,000 records, and that's within the 1.5 standard deviations, whatever I usually collect every day. Yes, the records are of these type. I got 10 records from people with the flu. I got 100 records from people with this illness, and that's normal. That's statistically normal for this time of the year. My data looks normal. My metrics in my model look normal. Everything is good. And as soon as things start to get out of whack, now I'm getting a different density of data than I normally get. Now I'm starting to be out of my sphere of influence. My statistical process control indicators are going yellow and red. Now I should be saying I'm starting to lose confidence in what my AI system is doing, because it is now touching realm of experience that it hasn't had before. And I think this is how we can start to put guardrails on AI. And this is what Daisy does. We're recommending promotional prices for a customer in retail for a product. We'll say this product, historically, all the promotional prices were typically $1.99 plus or minus 1.5 standard deviations. In the last 10 years, that's what you promoted it at. And so when Daisy's AI system recommends you should promote it at 62 cents. Well, that's way outside of 1.5 standard deviations. Okay, if something's wrong here, we're going to correct that. There's two approaches. You can either shut the model off, like in the factory, it's red, danger, 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 shut the model off. In the case of business, it's not going to blow up a plant, so I don't necessarily shut the model off, but I can now correct it. Let's correct that price back to the known good value, that I shouldn't do 62 cents because that's outside of the known control values. I know that $1.99 is an average price. So maybe I should adjust my recommended price to be within the guardrails so that I'm not doing anything different. I can either go back and diagnose what's going wrong with the model or with the recommendation, go look through the whole data engineering flow from when the data came in to when the model was run. Hopefully, if I have statistical process control, I don't have to wait to get to the end to see an anomaly. I should capture it somewhere along that processing workflow that we have, or pipeline, as modern engineers and data scientists call these things. Somewhere in the pipeline, we saw warning flags that got way before the end. We shouldn't wait to the very end. But if we did make a recommendation that was way out of normal experience, then we set guardrails that we're not going to allow any recommendations we make to be outside of these control limits. In fact, when you first start, you might even narrow those control limits more. And those control limits for sure want to be inside of our sphere of experience, where we are confident, where we have lots of data, lots of past points, where we know and understand the behavior. And so over time, if we manage these guardrails, we can push the guardrails a little bit. We could say, okay, we don't want to over constrain the system, because if we over constrain the system, we're only going to live within our lived experience and not learn anything new. We now, with some percentage of our decisions where there's low risk, we're going to expand our experience. We're going to try decisions that are outside of our experience by a few percent. We're going to relax those guardrails. We're going to go from 1 step to 2 steps, not to 10 steps as the baby. We're going to slowly say, let's go plus or minus 15% instead of plus or minus 10%. And we see, our logic still works in this realm. It's not in the realm of insanity. Okay. And over time, we can do this on all the decisions. Our system is making millions of decisions. It sounds like a tedious process to do this one by one. You're not manually doing this. This is your system should have these control knobs in your AI system. Remember, AI is a system. It's not just a mathematical model. We can control these statistical process control knobs to allow our domain of experience to grow. And then we can test and learn, right? And as we test and learn, we can see that our domain of experience expands. The applicability of our system can expand to a larger and larger universe, and more new decisions that we may have never made in the past. And so that's what I would say, some kind of statistical process control like that, or some type of control system like that we can put into place. That's something that's very important to do and slowly grow your experience. And I think a lot of the software we saw, some chatbots that came out like a couple of years ago were making racist slurs and swearing obscenities and things like that. And I think that's because there were no guardrails on the conversation. So even like with ChatGPT, that's released out there, there doesn't seem to be any guardrails on it. You could ask it any question. There are some controls I've seen like OpenAI. I asked how do I make a nuclear fusion bomb? It said, sorry, I'm not able to answer that question. So they have put some guardrails on it, but this idea of where do you think that it will be most likely to be correct, because there's a lot of data that it's been trained on. So I think there's probably a density map in that large language model of where that model feels confident and where it doesn't feel confident. We know it can't do a priori right or wrong, but where can we be confident that we have enough data that we feel pretty good about the predictions that it makes? So I think these are important concepts to consider. So that's one thing. To touch very briefly on repeatability is another area. So a lot of these models that we build are not deterministic in that they have some random number generator somewhere in the code, so that if you run the software 2 times in a row because there's a random number generator, I'm taking a random guess and then I'm iterating from a random guesses, you may not get the same answer 2 times in a row. So if I ran my software, I'm optimizing, so optimization software makes a guess, measures the accuracy, and then based on the error, it adjusts the guess and keeps adjusting the guess until it gets better and better. If you're doing gradient descent, you think of a parabola. If you're following the slope of the parabola, you're going down, down, down the slope. And as you're getting better and better, getting closer to the minima, you're looking for the minima of the parabola. Let's say you're following the slope of the parabola to go down to get less and less and less. And so that's kind of gradient descent. You're following the slope of the hill to find the bottom of the hill, right? So that's kind of how optimization works, right? So if you start at a different point on the parabola, because you're saying kind of randomly guess where the minimum, the bottom of the hill is, and 2 times in a row you start at a different point, if you do 100 steps towards the bottom, after 100 steps, you might be in 2 different places. And if you only have time to do 100 iterations of that, you may not find the minimum, the bottom of the hill in 100 guesses. So you might have 2 different answers depending on where your random guess was. So what do you do then, right? If you do it 10 times, what do you do then, right? So this is, again, another question of guardrails is if I get the wrong answer, if I get a different answer running my software multiple times, I'm not sure how many people actually would run their software multiple times or create their model. I think there is the concept of Monte Carlo repeats. When you're training your models, you should be doing Monte Carlo validation and cross-validation, Monte Carlo repeats and cross-validation. But the idea of doing many Monte Carlo experiments to make sure that you're, again, getting a safe result. And again, you can put the statistical process control boundaries around this Monte Carlo analysis. And Monte Carlo analysis is a form of statistical process control as well. So, putting that framework into the thinking and practice is important, not only on the model training, which is typically a lot of talk about, but on the model outcomes. What do we do with the outcomes and using them, making sure that we're not doing anything dangerous? That's what I had to talk about today. Hopefully that's helpful. Some very micro level detail, again, bringing in industry experience. We've got a lot of experience in statistical process control and manufacturing industries and engineering, and this is not a new field. So let's leverage what we already know. And maybe that's one idea, not the only idea. And there's probably many people who are already thinking about this topic and have a lot of experience as well. So we'd love to hear from you. Yeah, let's leverage what we know, bring this into the conversation again, take some of the fear away from the lay people who think that this is uncontrolled. We know how to control these systems. We can very safely implement these sophisticated AI solutions, which could do great things for humanity, and we can control them in a way that they don't do anything dangerous, as long as we continue to leverage the wealth of knowledge we have in many other disciplines that do these things already today. So hopefully that stimulates some ideas and conversation. As always, feel free to reach out if you violently agree with me or you violently disagree with me. I'm more than happy to follow up and have a conversation. Follow us on YouTube and Spotify. Share with your friends if you found this helpful, and look forward to hearing back from you. Thanks so much.